Find the newest building on your street. Maybe it went up 5 years ago, maybe 10. Now consider this. The concrete holding it together has an expected lifespan of somewhere between 50 and 100 years before it begins to seriously degrade. The steel reinforcement inside it starts to rust the moment moisture finds a crack. The building you are looking at right now, built with the most advanced construction materials in human history, will likely need significant structural intervention within your lifetime. And then there is Göbekli Tepe, a site in southern Turkey where somebody 12,000 years ago, before writing, before the wheel, before agriculture, before any of the things we associate with civilization, carved limestone pillars weighing up to 20 tons, transported them without wheeled vehicles, and assembled them into complex circular enclosures that are still standing today. Not restored, not reconstructed, still standing. So what did ancient builders know that our concrete somehow forgot? The answer is a masterclass in engineering that modern construction is only now beginning to fully appreciate. Start with the basic problem. When you build something, you are fighting two enemies. Gravity pulls everything down. Time breaks everything apart. Modern construction fights both enemies with brute force. More material, more steel, more chemical binding agents. The result is structures of extraordinary short-term strength that accumulate stress internally until they fail. Ancient builders took a completely different approach. Instead of fighting gravity and time, they worked with them. And the results have outlasted everything we have ever built. The first thing to understand is why the absence of cement is not a weakness. It is an engineering advantage. Dry stone construction, the technique of stacking and fitting stones without any binding material whatsoever, produces a structure that behaves fundamentally differently from cemented construction under stress. When a cemented wall is hit by seismic activity, thermal expansion, or ground movement, the rigidity of the cement means the stress has nowhere to go. It concentrates at weak points until something cracks. A dry stone wall, by contrast, is not rigid. It is flexible. Each stone can shift microscopically in response to stress, redistributing the load across the entire structure rather than concentrating it at a single point. The wall breathes, and walls that breathe do not crack. Dry stone structures in earthquake zones across the Mediterranean have survived repeated seismic events that destroyed every cemented building around them, not because they are stronger, but because they are smarter. But flexibility alone does not explain Göbekli Tepe. The site presents an engineering puzzle that has occupied archaeologists and structural engineers for decades. The pillars at Göbekli Tepe are not stacked stones. They are single carved limestone monoliths, some reaching 6 meters in height and weighing up to 20 tons, shaped with precision using stone tools, transported from quarries up to 500 meters away, and erected vertically in prepared sockets cut into the bedrock. This was accomplished by a population of hunter-gatherers, who, by every model of social organization we previously accepted, should not have had the surplus labor, the organizational capacity, or the engineering knowledge to attempt anything remotely like it. The site did not just revise our understanding of ancient engineering, it demolished our entire timeline of human cognitive development. People this organized, this architecturally sophisticated, and this capable of sustained coordinated effort were supposed to appear thousands of years later. Göbekli Tepe existed before the script was written.
The question of how those pillars moved has consumed researchers for years. Experimental archaeology, the practice of actually attempting to replicate ancient techniques with period-appropriate materials, has produced some extraordinary answers. A team of researchers in 2017 demonstrated that a 20-ton monolith could be moved by a group of between 15 and 20 people using nothing more than wooden sledges, ropes made from plant fiber, and carefully prepared earthen ramps. The key insight was lubrication. Wet clay applied beneath the sledge runners reduced friction dramatically enough that the force required dropped into the range achievable by a coordinated human team. No machines, no wheels, just physics applied with precision. The ancient builders didn't overcome the weight problem. They made the weight irrelevant. Now, here is where the engineering gets truly extraordinary. On the island of Malta,
sitting in the middle of the Mediterranean, there were two temples called Ggantija. They were built approximately 5,500 years ago, making them older than Stonehenge by over 1,000 years, and older than the Great Pyramid by almost 900 years. They are the oldest freestanding stone structures on Earth, and they were built by a civilization about which we know almost nothing, using limestone blocks, some of which weigh over 50 tons, fitted together with a precision that requires no mortar to maintain structural integrity after 5.5 millennia of Mediterranean weather, earthquakes, and time. The people who built Ggantija did not leave a written record. They did not leave a name. They left only the buildings. And the buildings have outlasted every empire that rose and fell in the centuries since they were completed.
Stonehenge presents a different set of engineering achievements, and some of them are genuinely startling, even by modern standards. The sarsen stones at Stonehenge, the large upright stones that form the outer ring, weigh up to 25 tons and were transported approximately 250 kilometers from their quarry at Marlborough Downs. The blue stones of the inner ring came from the Preseli Hills in Wales, a distance of approximately 250 kilometers. But the transportation is not the most impressive engineering feat at Stonehenge. The most impressive is the joinery. The lintels, the horizontal stones that sit across the top of the uprights, are not simply rested in place. They are locked. Each lintel has carved mortise and tenon joints on its underside, fitting precisely into corresponding raised tenons carved into the tops of the upright stones. The same joinery technique used by carpenters to connect wooden beams, applied to 25-ton limestone blocks, carved with stone tools, with tolerances precise enough to have survived 4,000 years of British weather without shifting. Whatever tool we use to measure ancient cognitive capability, Stonehenge keeps exceeding it. The acoustic engineering at Stonehenge is less well known, but equally remarkable. Studies conducted by acoustic scientists have found that the stone circle, in its original complete configuration, would have created a reverberation effect that dramatically amplified and transformed sound within the circle while dampening it outside. Voices, music, and ritual sounds produced inside would have carried a resonant, almost supernatural quality to anyone standing within the ring. This was not accidental. Acoustic analysis of other megalithic sites across Europe has found similar properties, suggesting that the acoustic behavior of enclosed stone spaces was understood, valued, and deliberately engineered into these structures. Ancient builders were not just managing gravity, they were managing sound.
Then there is the polygonal masonry of the Inca Empire in Peru, which represents perhaps the most visually astonishing dry stone engineering ever produced. At sites like Sacsayhuamán above Cusco, enormous stone blocks weighing up to 120 tons were cut into complex, irregular polygonal shapes with multiple faces and angles, then fitted together so precisely that a sheet of paper cannot be inserted between them. Not a single block is the same shape as another, and yet every block fits its neighbors perfectly on every surface. Modern stonemasons examining these walls with laser scanning equipment have found tolerances of less than 0.5 millimeter across joints spanning several meters of stone face. This level of precision using steel tools and modern measuring equipment would be considered exceptional. The Inca achieved it with stone tools and methods that have never been fully reconstructed. Peruvian structural engineers studying Sacsayhuaman after the 1950 Cusco earthquake found that the Inca walls survived intact, while the Spanish colonial buildings constructed directly on top of them using European masonry techniques collapsed. The conquered engineering outlasted the conquerors. The pyramids of Egypt sit at the extreme end of ancient engineering achievement, and the binding material question is central to understanding them. The Great Pyramid of Giza was not built without binding material. It was built with a lime-based mortar applied between certain stone courses. But that mortar is not the modern Portland cement we use today, and the difference is critical. Ancient Egyptian lime mortar is flexible, breathable, and chemically compatible with the limestone blocks it binds. It expands and contracts with the stone. It allows moisture to pass through rather than trapping it. Modern testing has found that the mortar used in the Great Pyramid has maintained a compressive strength of approximately 2,000 pounds per square inch after 4,500 years.
Portland cement, our modern standard, typically degrades to below that threshold within a century under similar conditions. The ancient Egyptians didn't use an inferior version of our cement. They used a superior one. We replaced it with something cheaper and faster, and we are still paying the consequences.
And modern engineers have noticed, in the last 2 decades, a growing field of research called archaeomaterial science has emerged specifically to study ancient construction materials and techniques for modern application. Roman marine concrete, a mixture of volcanic ash, seawater, and lime used to build harbor structures 2,000 years ago, has been found to actually grow stronger over time as seawater causes new mineral crystals to form within the mixture. Modern concrete crumbles in seawater. Roman concrete thrives in it. Research teams at universities across Europe and North America are now actively attempting to replicate Roman and ancient Egyptian formulas for modern construction use. The field has a name. It is called biomimetic construction, and its primary source material is the ruins of civilizations that fell thousands of years ago. What connects all of these achievements is not superhuman strength or lost technology or alien intervention, 3 explanations that require us to believe ancient humans were less capable than they were. What connects them is sophisticated observation, accumulated knowledge, and an engineering philosophy fundamentally different from ours. Modern construction optimizes for speed and short-term performance. Ancient construction optimized for permanence and environmental compatibility. Where we add material to overcome a force, they studied the force until they understood how to redirect it. Where we bind elements together rigidly, they understood that the right kind of flexibility is stronger than any bond. Go back to that building on your street, the one built with the most advanced materials in human history. Its concrete is already counting down. Somewhere in southern Turkey, a set of limestone pillars carved by people who had never seen a written word, never used a metal tool, and had no concept of a calendar is going to be standing long after that building is rubble. The most enduring lesson ancient engineers left us wasn't carved into stone. It was the stone itself, still standing after 12,000 years, waiting for us to ask the right questions. If this changed how you think about the buildings around you, let me know in the comments which ancient structure surprised you the most, and subscribe to Stone Age Engineers for more stories about the most ingenious builders who ever lived.